For our first type of solving log equations, we have equations of the form log equals number. In each one of these problems, you have to have a constant term located in the problem, and we're going to isolate the constant term on one side and the log on the other side in a single logarithm. Just to remind you of the steps that we're going to follow, step 1 says to condense to a single logarithm. For example, if there are 2 logarithms, you need to get them on the same side and condense them down to 1, so that it's in the form log equals number. Then step 2 says change the log to exponential form, where we can solve and then check the argument. So our first problem already is in a single log equals a number. So step 1 is already completed for us because I've isolated the constant term. Step 2 says we change the equation from log form to exponential form. So my base is an invisible 10 here, so I'm going to rewrite this equation as base 10 raised to the 1 power because the argument and the exponents are changing sides here. So 10 to the 1 equals x minus 3. So that's step 2. Step 3 says to solve. That's fairly simple at this point. And then I get the answer x equals 13, which is my potential answer. I say potential because you have to check to make sure that your answer doesn't make the argument 0 or negative. And the reason that the argument cannot be 0 or negative is because that the domain of a log function is from 0 to infinity. So we cannot have any negative or 0 arguments. So the only checking I'm going to do is plugging it back into the original problem and making sure that when I plug x in for 13, that 13 minus 3 is 10. Now if you'd like to check to make sure log 10 is equal to 1, you're welcome to, but that is not the check you're required to do. The only check you're required to do is making sure that the 13 minus 3 is something greater than 0. Now if you're interested, we can open up our graphing calculator and just type log. Notice it's log base 10, so I can just use log 10, and it does happen to be 1. So we did check our work for accuracy as well as for extraneous solutions. So my solution here is 13. Looking at our next problem, we're trying to make sure that we have a constant term, and we do. We have a 2, which is just a number. It doesn't have an associated log. So what I'm going to do is I'm going to take step 2 that says change my log form to an exponential form, because step 1 is already done. I already have log equals a number. So when I changed to the exponential form, my base was 4. So that's my base of the exponent, raised to the 2 equals the argument x plus 3. Lastly, I'd like to solve, and I get x equals 13 again. That's just a coincidence that it happened to be the same. The last thing I'd like to do is to check to make sure that when I plug 13 in for x, that the entire argument is neither 0 nor negative. So when I have 13 plus 3, that's 16, so log base 4 of 16 is 2. And that actually does also check out for accuracy because 4 squared is 16. So my final answer is 13. On our next problem, I want to make sure that it's the right type of problem by making sure that we have a constant term, and I certainly do. And I have 3 ln 2x equals 12, and the 12 is a constant term, and so therefore it is of type 1. Although, when I say condensed to a single logarithm, I do have a single logarithm here, but it is not condensed. And the reason it's not condensed is because we have a multiply by 3 in front. There's 2 different things we could do with this 3. We could, because it's a coefficient in front of a log, I could move it to the exponent. But there's a simpler answer we could do to get rid of the 3. And the simple answer is just divide both sides by 3. Which leaves us with ln of 2x equals 4. That's much more simple than creating a cube, and then we have to deal with the cube later. And so dividing by 3 divides 12 evenly, so it's actually a much simpler method than trying to move it to the exponent. So that was step 1. I have now condensed to a single logarithm with no coefficients in the front other than 1. Step 2 says change my log form to an exponential form. So I have a base e here, so that gives me e to the 4 equals 2x. The 4 and the 2x switch sides and the 4 becomes the exponent. Now I still haven't solved for x, and the way I have to solve for x now is to divide both sides by 2. So my answer is x equals e to the 4 over 2. Now e to the 4 is a positive number because e is a positive number. When I raise it to the 4th power, it's another larger positive number, and a positive number divided by 2 is still a positive number. So I know that this is non-negative. So when I plug in this non-negative answer into my original problem, 3 times ln of 2 times e to the 4 over 2 is supposedly equal to 12. The 2's inside my argument can divide out, and I just get 3 ln of e to the 4. E to the 4 we've already said is positive, so this is as far as I really need to go. You're welcome to check it. You can type this in the calculator to make sure that it works. But that's as far as you're required to go. All you need to do is make sure that this e to the 4th over 2, when you plug it in, does not make the argument 0 or negative. So I'm just going to leave my answer in exact form. You could try to type it in the calculator, get a decimal approximation, but this is actually a better way of answering this problem. On the next problem, we do have a constant 3. So this is of the form log equals number. Although step 1 tells me that I need to condense down to a single logarithm, and I have 2 logarithms at the moment. So to condense the 2 logs, I'm going to use the product rule, which gives me log base 2 of x times x minus 7 equals 3. And we could have actually distributed that to get x squared minus 7x. Step 2 says change from log form to exponential. My base here is 2, so that gives me 2 raised to the 3rd power equals x squared minus 7x. And now I'm left with a quadratic equation, which I can solve by factoring. I'm going to move the 8 over to the other side. So I factor and get x minus 8 times x plus 1. So my two potential answers are x equals 8 and x equals negative 1. Now I say potential because I have to check both answers. You cannot just say, well, 8's positive and negative 1's negative, so therefore that's not right. And you have to make sure that when you plug in 8 to both terms that it doesn't make either negative. So I have log base 2 of 8 plus log base 2 of 8 minus 7, supposedly equal to 3. This argument is positive. 8 minus 7 is 1. 8 is positive. So 8 checks out as non-extraneous. I didn't check for accuracy, but I did check for extraneous. On my next problem, I have log base 2 of negative 1 plus log base 2 of negative 1 minus 7 supposed to equal to 3. And right off the bat here, my argument of the first term is negative. The argument of the second one is even more negative, but it really doesn't matter. If one of the two is negative, then the x equals negative 1 is an extraneous solution, and I'm going to cross it out. So the only solution that works is the positive 8. On our next problem, we have log base 4 of x minus 3 equals 2 plus log base 4 of x plus 3. Some students may look at this and say, oh, that's a log equals log problem, because there's a log on the left and a log on the right. But this is of the first type, log equals number, because one of the terms is a constant. So in order to get this to look more like log equals number, I'm going to move the log base 4 of x plus 3 to the other side, which leaves me with log base 4 of x minus 3. I'm going to subtract the other log from both sides, or using transposition, if you move it across the equal sign, it changes its sign. And now this looks very similar to the one we just did on our previous example. Next, I would like to condense the left side to a single logarithm. Now, because there is a subtract sign in between the first and the second log, I am going to use the property that says I'm allowed to divide the arguments, x minus 3 over x plus 3. That's still equal to 2. Now it is of the form log of the argument equals a number. So I'm going to change it into exponential form. For the base 4 raised to the exponent 2 is equal to the argument. 16 is equal to x minus 3 over x plus 3. One simple way to solve this is just to put the 16 over 1 and cross multiply, which will get me 16 times x plus 3 equals 1 times x minus 3. Distribute, I'm getting 16x plus 48 equals x minus 3. Moving the x's together on one side, I'm getting 15x on one side. Subtract the 48 to both sides, I'm getting negative 51. Then I'm going to divide both sides by 15. And I believe that reduces here. So my final answer is x is equal to, divide the numerator and the denominator both by 3, negative 17 fifths. I believe this to be my potential answer. Now I say potential answer because I have to check my work. And in order to check my work, I need to make sure that when I plug it back in, the argument is not negative. So going ahead and plugging it in, I'm getting log of negative 17 fifths minus 3 is supposedly equal to 2 plus log base 4 of negative 17 fifths plus 3. Now I can already see here that negative 17 fifths minus 3, although I didn't do the work, a negative minus 3 is still going to get you a negative argument. So that means that this is not a good answer. So I'm going to cross it off, and my solution is going to be no solution. So that concludes our type 1 problem solving log equations where the log is equal to a number, where we have a constant in the equation. Our second type of solving log equations is where we have the form log equals log. There's a log on the left side, there's a log on the right side, and there are no constants anywhere to be found inside the equation without an associated log. The steps are very similar. Step 1, condense to a single logarithm. Step 2 is the difference step. Step 2 says if the log base b of m equals log base b of n, then if the bases are the same, then your arguments have to be the same. This is very similar to the type 1 problems in the exponential equations. So step 2, instead of changing to log form, we're going to set the arguments equal to each other. Step 3 is the same, solve and check. On our first problem, I have two logs on the left-hand side, so I'd like to combine them using my product rule. Log base 2 of 5x minus 15, I'm multiplying the two arguments together, equals log base 2 of x plus 5. Notice that I have log equals log. The bases are the same, and because I have log equals log and the bases are the same, that must mean that the arguments are equal to each other. So I'm going to set the two arguments equal to each other. And then I solve for x. Which leaves me with 4x equals 20. Divide both sides by 4, and my potential answer is 5. To check the potential answer, I need to plug 5 in to each of the arguments. The first one, log base 2 of 5, doesn't have an x, so we don't have to worry about that one. Log base 2 of 5 minus 3. 5 minus 3 is 2, positive. It is supposed to be equal to log base 2 of 5 plus 5. 5 plus 5 is 10, again positive. That is the only thing I have to check. You can go a little bit further and check for accuracy if you would like to, but you don't have to. On our next problem, again we have two logs being added equals another log. There are no constant terms in this equation whatsoever. So this is going to be a log equals log equation. So I'm going to add the two logs together. Because I'm adding two logs, I get to multiply their arguments. I'm going to distribute in here. I get x squared minus x. Notice that I have log of an argument equals log of an argument, and there are no constant terms here whatsoever. Because the log base e and the log base e have the common base, or the same base, I can take the two arguments and set them equal to each other. Some students like to say, oh, because the ln's are canceling each other out. Well, technically they don't really cancel each other out. What you're doing is you're setting the arguments equal to each other, but a lot of students like to think about it that way. The correct mathematical way of saying it is you're setting the arguments equal to each other. Because it's quadratic, I'm setting equal to 0 to solve by factoring. And it looks like my two potential answers are 0 and 3. To check both of my answers, I'm plugging them back in. ln of 0 minus 1. 0 minus 1 is negative. Right off the bat, this is not a valid log, so I don't even have to keep going. I know that 0 cannot be a solution. Let's check 3. ln of 3 minus 1. Well, 3 minus 1 is 2, which is positive, so that's good. Let's keep going. Plus ln 3. Well, 3 is positive, that's good. Equals ln of 2 times 3. Well, that's 6, so that one's good. That is as far as you need to check. 0 is extraneous because when you plug in 0, you get a negative argument, and there's no such thing as a log of a negative. So 0 is extraneous, and we keep the 3 as our solution. For our last example, we have one log on the left-hand side, but two logs on the right. So I'm going to take the two logs on the right and condense them down to a single logarithm by using the quotient rule. Because we're subtracting, we get to divide the arguments, or take the quotient of the two arguments. So we have log base 10 of x plus 1 equals log base 10 of x plus 9 over x. You don't really have to write the base 10, but I'm just trying to emphasize that the bases are the same. I have log equals log. There is no constant term here whatsoever. So because it's log equals log, I can take the two arguments and set them equal to each other, which leaves me with x plus 1 equals x plus 9 over x. One fast way to solve is to put the left-hand side over 1 and cross multiply, which leaves me with x times x plus 1 equals 1 times x plus 9. Looks like my x's are going to subtract off here, leaving me with x squared equals 9. Next, I can take the square root of both sides, and my answer is positive 3 and negative 3, because when you take the square root of both sides, you take the plus or minus part. Before I can say that these are my two answers, I have to check my work. And the only reason I have to check my work is to make sure the arguments are not 0 or negative. So when I plug in, we'll start with 3. 3 plus 1 is positive, that's good, equals log of 3 plus 9. 3 plus 9 is 12, that's positive, minus log of 3. 3 is positive. Notice I'm only checking the arguments, or the thing inside the parentheses with the log. So 3 looks like it's a good solution. Let's check negative 3. Log of negative 3 plus 1. Negative 3 plus 1 is negative 2. And I know this keeps going, but I'm not going to continue to check because the first argument is negative, so I know automatically that negative 3 is not a valid solution. So because it's not a valid solution, the only solution I can keep is the positive 3. And that concludes our lesson on solving exponential and logarithmic equations. We had two types of exponential equations where the bases could be rewritten as the equal bases, or where the bases could not be rewritten as equal bases. We had two types of log equations that we solved, log equals number and log equals log. And don't forget to check all of your log equations to make sure that the arguments are neither 0 nor negative.